Alright, let's go get started with this Math221 Midterm 2. For question 1, we want to compute the following definite integrals. For question A, we have the integral, which I'll call I, from 1 to 3 of 3x to the 4th plus 2 over x cubed, which I'm going to rewrite as 2 times x to the minus 3, plus the square root of x, which I'll rewrite as x to the 1/2, plus cosine x dx. And now for this one, the key is just remembering your integration rules. So we can write this as the integral. And remember, integrals are additive, so you can just look at the integral of each part that's added together separately. So first off, we have 3 times x to the 4th. So we can write a 3 out front. And then the integral of x to the 4th, well, you can add 1 to the power, making it x to the 5th, and then divide by that. So 1/5 times x to the 5th. For this next one, we have plus 2 times the integral of x to the minus 3. So add 1 to minus 3, we get minus 2, and then divide by that. So we get, divide it by minus 2 times x to the minus 2, just like that. And now for the next one, we have x to the 1/2. So for this one, we are going to add 1 to 1/2, which gives us 3/2, and then dividing by 3/2 is the same as multiplying by the reciprocal of 2/3. So 2/3 x to the 3/2. And of course, you can always check these power rules by differentiating them. Now the derivative of cosine x, hopefully you remember, that's just going to be a positive sine x. You can definitely mix up those negatives if you're not careful. And now, let's go ahead and integrate this from 1 to 3, just like that. So now, we can rewrite our integral. Let's go ahead and kind of simplify and substitute in numbers all at once. So when we put in 3, we're going to get this first bit turns into 3/5 times 3 to the 5th, right? Plus this 2 divided by 2 is going to turn into a 1, and of course we have a negative out front, so we'll subtract 1 over x squared, which is 1 over 3 squared. And then we're going to add to this 2/3 times 3 to the 3/2. And lastly, we are going to add sine of 3. Now to subtract the 1 portion, well, we're just going to get 3/5 minus 1, right, plus 2/3 plus sine of 1, just like that. And now let's go ahead and start simplifying just a bit. So in this first brackets, 3 times 3 to the 5th is going to be 3 to the 6th over 5. And then we are going to subtract from this 1 over 9. We're going to add this 3 to the 3/2 divided by 3. Well, that's going to turn into a square root 3, or 3 to the 1/2. So we'll write that as 2 times the square root of 3, and that's going to be over 1, right? And then we add sine of 3. Now subtracting 3/5, adding 1, I'm just distributing the negative, subtracting 2/3, and subtracting sine of 1. Now let's go ahead and combine some fractions, because they're not very clear how much we need to simplify. So the first thing, let's get all of these fractional terms, the non-trigonometric ones, over a common denominator. So we have a 5 and a 9, so let's put everything over 45. So this first one is going to be 3 times 9, which will be 3 to the 8th, over 45. This is minus, we'll get 5 over 45 for this one, plus this is going to be 2 times, we're multiplying by 9, so this 3 to the 1/2 will turn into 3 to the 5/2, sorry. And then we're going to multiply by 5, divide everything by 45. And then next up, we are going to subtract 3 times 9 is going to be 3 to the 3rd. over 45. Adding 1 is plus 45 over 45. And then subtracting, we're multiplying this by 15. So this will be 10 times 3 over 45. And then add sine of 3, subtract sine of 1. Now let's go ahead and combine all of our fractions. We are going to get 3 to the 8th. And I'll keep all of the 3's kind of in a similar area. So this is going to then be, let's add this plus 10 times 3 to the 5 over 2. And then subtract 3 to the 3rd. And then subtract 10 times 3. So those are all of our terms with 3. And then lastly, we have minus 5 plus 45. That's going to turn into a plus 40. And again, all of this is over 45. Then we can just add sine of 3, subtract sine of 1. And let's see. We'll simplify one more time, I think. So we'll have the integral of, we'll keep this 3 to the 8th term, plus 10 times 3 to the 5 over 2. And now over here we're going to simplify. So this minus 10 times 3, this turns into a 30. 3 to the 3rd is 27. So we are subtracting 30 and 27, which is minus 57, and we add 40. So that's going to end up being minus 17. All of that over 45, and then plus sine of 3, minus sine of 1. And that is our first integral right there. Just like that. Alright. Alright. For part B, we have, I'll call it I again, the integral from 0 to 1 of t to the 6th plus 4 times 3t minus 2. For this one, I think the easiest way to approach it is to just distribute these two parentheses terms, I suppose. So you have the integral from 0 to 1 of this is going to be t to the 6th times 3t, which is going to be 3t to the 7th, minus 2t to the 6th. Now moving on to this 4, we have plus 12t, and then minus 8. Now I'm just foiling these two terms, dt. And now for this, we're just going to use the power rule. So we'll have that this is going to be equal to, we'll factor out a 3, and then the derivative, so I'm sorry, the integral of t to the 7th, that's going to be 1/8 t to the 8th, minus 2 times 1/7 t to the 7th, plus 12 times 1/2 t squared, minus 8t. And of course, you could be simplifying these immediately if you want. I'm just writing it out, so it's hopefully a tiny bit more clear. We are integrating this from 0 to 1. So now I've got plenty of space, so let's go ahead and simplify this. We have 3/8 t to the 8th minus 2/7 t to the 7th plus 6t squared minus 8t. Integrated from 0 to 1, just like that. And now let's go ahead and put in these bounds. So when we substitute 1 in, we're going to get 3/8 minus 2/7 plus 6 minus 8. And then of course this 0 is going to cancel, so we're just subtracting 0 for this whole term, so we can ignore it. And now we just need to find a common denominator. So we have an 8 and a 7, so the least common multiple is going to be 56. So let's go ahead and multiply this first term above and below by 7. That's going to give us 21 over 56 minus, we're going to have to multiply this term by 8. We're going to get 16 over 56. And then adding, well, let's see. Let's go ahead and simplify this first, actually, so it's not super awful. Plus 6 minus 8 is going to be minus 2. And so this is going to give us 21 minus 16 will be 5. So we get 5 over 56. And then subtracting 56 times 2 is going to be 112. So we get minus 112 over 56. And this is just going to be equal to, let's see, negative 107. So negative 107 over 56, just like that. And that is our final answer for part B. Moving on to question 2, we want to find the antiderivative, which we'll call big F, of the function f of x equals 3x squared plus sine x. This satisfies the condition that big F of 0 is equal to 6. So let's go ahead and write out our first function. We have little f of x is equal to 3x squared plus sine of x. And so we know that the antiderivative of this is our big F, so let's go ahead and find that. So we have big F of x is going to be equal to the antiderivative, or the integral, of little f of x dx, which is just the integral of 3x squared plus sine x dx. And to integrate this, the first one is going to be the power rule, and this one, hopefully, or well, maybe you notice right away that this is just the derivative of x cubed, so the integral of this is going to be our x cubed. Of course, you could do it the full way using the power rule, 3x squared, well, the integral of this is going to be 3 times 1/3 x cubed, which is just going to be x cubed. Or yeah, of course, you can recognize that this is the derivative of x cubed is 3x squared. And then for our sine term, remember the integral of sine is minus cosine. The signs are going to flip from what you memorized for your derivative rules. So this is minus cosine of x, and of course, because this is indefinite, don't forget the plus c. And now the last step is we have our big F of x. We have to plug in this value to find the specific curve out of the family of curves. So we have that f of 0 is equal to 6. So this tells us that 6 is going to be equal to whatever we get when we plug 0 into this. So well, of course, that's going to be 0 cubed minus cosine of 0 plus c. And 0 cubed is just 0, so we can cancel this. Cosine of 0 is 1. So 6 is equal to minus 1 plus c, or in other words, we get that c is equal to 7. So now let's go ahead and write out our final equation for our antiderivative function. We have big F of x is equal to x cubed minus cosine x plus 7, just like that. And that's our final equation. So moving on to question 3. For this one, we want to find all the vertical, horizontal, and slant asymptotes of this function right here, if there are any, and justify our answers for each asymptote. So first off, let's go ahead and write out our function f of x, which is equal to x cubed plus 2x squared all over x squared minus 4. So now the first thing that I'm noticing here is we're going to be able to simplify this. So let's go ahead and rewrite this just a tiny bit. On the top, let's go ahead and factor out an x squared. We're going to get x plus 2. And on the bottom, you might be able to recognize this is a difference of 2 squares, right? This is x squared and this is 2 squared. So we can rewrite that as x plus 2 times x minus 2. Just as a reminder, in case you forgot, the difference of 2 squared, say we have a squared minus b squared, this is equal to a plus b times a minus b. You can, of course, check that pretty easily by distributing these two. And so now at this point, we can see that we can actually cancel out x plus 2, which means our function is going to be the same as x squared over x minus 2, ignoring the whole we have at x equals minus 2. Right, when they cancel, we're going to get a whole, which we're not concerned about for this problem, so f of x is going to be functionally the same as this right here. Or functionally might not be the best word. It's going to work the same as this. So first off, let's check for vertical asymptotes. And so remember, vertical asymptotes happen when, sorry, I gotta spell, that looks about right. Nope, not quite. Remember, vertical asymptotes happen when the denominator is equal to 0. So, when does this happen? Well, we have x squared over x minus 2. Well, when is x minus 2 equal to 0? And this is pretty easy. Just move the 2 to the other side. this is the same as x is equal to 2. So for this problem, it's going to be pretty easy. The denominator is equal to 0 at x is equal to 2. So there's a vertical asymptote at x equals 2. And next up, for horizontal and slant asymptotes, the way we check for those is, remember, you have one or the other. You can't have both a horizontal asymptote and a slant asymptote, at least going in the same direction. So the way you check for these is you look at the degree of the numerator and the denominator. So to have a horizontal asymptote, the degree, let's go ahead and write this out in orange. For a horizontal asymptote, the degree of the numerator has to be equal to the degree of the denominator. And for a slant asymptote, the degree of the numerator has to be 1 more than the degree of the denominator. So it's the degree of the denominator, maybe I'll say denom, so it's a bit more clear, plus 1. And so in this case, that's exactly what we have, right? We have the degree of the numerator, which is 3, right? That's just the highest power you have, is equal to the degree of the denominator, which is 2 plus 1. So first things first, let's say no horizontal asymptotes. Because the degree of the numerator is not equal to the degree of the denominator. Okay, and now what we can look for is our slant asymptotes. So I'll just put slant for now. And so the way we look for slant asymptotes, if you remember, is by doing our polynomial division. So all we're going to do is we're going to see what happens when we divide x squared by x minus 2. So we'll take x minus 2, and we are dividing x squared, which we'll write out as x squared plus 0x plus 0. And of course, actually, in this situation, you could divide x cubed plus 2x squared over by x squared minus 4, and that would give you the exact same result. That's going to be a tiny bit longer, though, because those degrees are higher. So we'll just do it like this. And so the way we're going to do this division is, first off, we have an x and an x squared. So we're going to multiply by an x. That's going to give us x squared minus 2x. And when we subtract, we'll get 2x plus 0. And so to get rid of this 2x, we're going to need a 2 in front of our x. So we'll go plus 2. That gives us 2x minus 4, which just gives us 4. And remember, we're not worried about this remainder. We're just looking at the result right here. And that's going to be our slant asymptote. So this tells us, whoa, that's a really bad W. We have a slant asymptote of y equals x plus 2. And that's going to be about all we need for question 3. I suppose we could write by polynomial division. And may as well be thorough, because the degree of the numerator is 1 greater than the denominator. You probably would have been fine with just that first sentence though. Alright, moving on to question 4. We want to find the slope of the tangent line to the curve 2xy plus x squared is equal to y squared plus 7 at the point 2, 3. And so the way that we're going to do this is with our implicit differentiation. So we have 2xy plus x squared, which is equal to y squared plus 7. And the reason I know we're going to use implicit differentiation is because there's no way that we're going to be able to isolate the y's from the x's very easily. You could try, but since we have an x and a y multiplied as well as a y squared, there's no way that you're going to be able to get that out cleanly. So the way we do implicit differentiation is we pick the variable we're differentiating with, and since we want to find the slope, that tells us we want to find dy dx, right? So we want to differentiate with respect to x, because that's the one on the bottom, right? So let's go ahead and differentiate. So I'll write that out as we're differentiating with respect to x, 2xy plus x squared, and we have to differentiate both sides. We're also differentiating y squared plus 7. So let's go ahead and do this. So I suppose I'll write it right over here. This is going to be the same as the derivative of 2xy with respect to x. Let's go ahead and factor out a 2 first. And now for this next one, we're going to use the product rule. So the derivative of x with respect to x, well, we can write 1. I'll go ahead and write dx over dx, right? We're the derivative of x with respect to x, which is just going to be 1. And then multiplied by the second term, which is y. Sorry, there should be parentheses here. And then we want to add to this, well, the derivative of y with respect to x, that's dy dx, times the first term, which is x. And I may not have said that in the easiest way, but hopefully by looking at it, you can kind of see what I'm doing. I take the derivative of the first term with respect to x, multiply by the second, and then I take the derivative of the second term with respect to x, multiply it by the first term. Now the derivative of x squared is going to be 2x. And again, I'll go ahead and write dx over dx, but we of course know that this is going to simplify to 1. And this is equal to the derivative of y squared. That is going to be 2y times dy dx. And plus 7, the 7 goes to 0. So I'll go ahead and write it just for completeness. And now let's go ahead and rewrite this. We get 2y plus 2x dy dx. I'm just distributing that 2 into these parentheses. And then we go plus 2x is equal to 2y dy dx. Now let's go ahead and move this 2x dy dx to the other side, because we're going to want to factor. So this is the same as, and while we're at it, we can see all of these terms have a 2. So let's just cancel those out by multiplying everything by 1/2. This will give us y plus x, and then on the other side, we'll get y times dy dx minus x times dy dx. So I did kind of 2 steps there. I moved this term to the other side, and I divided everything by 2. So now let's go ahead on this right side, factor the dy dx out. So we get, I'm going to flip it to x plus y just because that looks nicer to me. We have x plus y is equal to dy dx times y minus x. And now last thing to do is divide both sides by y over x. We get dy dx is equal to x plus y over y minus x. So remember, we're trying to find the slope, which is dy dx, at the point 2, 3. So let's go ahead and plug in 2, 3. Suppose I'll denote it as dy dx with the subscript 2, 3. This is going to be equal to 2 plus 3 over y is 3 minus x is 2, which gives us 5 over 1 which just gives us 5. And so the slope at the 0.23 is just going to be 5. And that's it for question 4. Alright, so for question 5, we have that Sally is standing at the top of a 40-foot tall lighthouse and pulling a rope which is attached to a boat in the water below. So we have Sally up here, the boat down here, and she is pulling the rope at a constant rate of 5 feet per second. So while we read this, let's go ahead and label some things. Let's call this distance of the rope, we'll call it R, and we know that she is pulling at a rate of 5 feet per second. So let's say the change in R with respect to time, well, that's going to be minus 5 feet per second, right? Because she is shrinking R as time goes on. This rope is going to get shorter as she pulls it behind her. And now the question is, how fast is the angle between the rope and the water changing? So we'll call that theta down here, at the moment when the boat is 30 feet horizontally away from the lighthouse. So 30 feet horizontally is down here. And we also have that it is a 40-foot tall lighthouse. Okay, 40 feet. And so let's go ahead and start setting some things up. So for this one, the thing we want to notice here is we have a couple of different things. We have theta, which is what we want to find, and we know the hypotenuse the best out of anything. We know the rate of change of the hypotenuse, which is just this rope, and we also know that the overall height, or the opposite side, is staying the same. So we want to find a trigonometric function that relates the opposite side to the hypotenuse, and the one that we're going to use to do that is, of course, sine. We know that sine theta is equal to the opposite over the hypotenuse. And in this case, the opposite is a constant, 40 feet, and the hypotenuse is, we'll just call it r for the radius. The reason we don't want to use this 30 feet at the bottom, even though I labeled it as well, is because that's changing with respect to time, whereas the height, or the opposite side, is not. So we're gonna be able to simplify it down to one variable. So now at this point, we're going to use our implicit differentiation again. We're going to differentiate everything with respect to t. So the derivative of sine theta with respect to t, that's just going to be cosine theta times d theta dt, right, by the chain rule. And this is going to be equal to, let's factor out a 40. So we have a 40 out front here. And then what is the derivative of 1 over r? Well, I'll go ahead and write it out in orange here. 1 over r is equal to r to the minus 1. And so by chain rule, right, we can bring that minus 1 down. We get, suppose I'll write it up here, the derivative, let's say with respect to r for now, of r to the minus 1 is just going to be equal to minus r to the minus 2. And so when we look at it with respect to t, we're still going to get minus r to the minus 2. And we just have to also multiply by dr over dt, just like this, by the chain rule again. So now let's go ahead and simplify this just a bit. We have d theta dt, which remember is what we want to find. We want to find how that angle is changing. Let's go ahead and move this cosine to the other side while we're here. We have 40 over cosine theta times, this becomes 1 over r squared, so times a minus 1 over r squared times dr over dt, just like that. And so now we're ready to start finding some values. So we know the length, we don't know the length of the rope. We're going to need to find that. We're also going to need to find cosine theta, but we do know dr dt, right? That is our minus 5 feet per second. So the way we're going to do this is we want to find r when the height is at 40 and the distance horizontally is at 30. And we could use the Pythagorean theorem, right? X squared plus y squared equals z squared. Or what we could notice is that this is actually a special triangle. This is one of our 3, 4, 5 triangles, all scaled by 10. So we know that in this case, r is actually going to be at 50 at this specific moment in time. And again, you could absolutely use the Pythagorean theorem. And the other thing, for cosine theta, well, cosine theta that is equal to the adjacent over the hypotenuse. And in this case, we know both of those quantities. So the adjacent is 30, the hypotenuse is 50, so cosine theta is just 30 over 50. So let's go ahead and rewrite d theta dt. So d theta dt is going to be equal to 40 over 30 over 50 times a minus 1 over r is 50, so we get over 50 squared, times dr dt is minus 5. I'm leaving out the units for now, and we'll come back to them at the very end. So this is going to be equal to 40 times minus 1 is going to be minus 40, but times a minus 5 is going to cancel out. And so for now, actually, let's just write this as 40 times 5. Right, the two negatives canceled. Then on the bottom here, this 50 is going to cancel one of these 50s. So we're left with 30 times 50, just like this. So now let's go ahead and cancel out one of these zeros, right, because you can imagine factoring out a 10. And let's cancel out this 5 and this 5 right here. And we're left with 4 over 30, or this is also 2 over 15. And this is going to be in radians per second. Now, if you want to take a quick look at the units, we have feet per second right here. The cosine theta, or I'm sorry, let's do this r squared. This is going to be 1 over feet squared right here. And this, of course, is in feet up here. And then cosine theta, that you just want to think of as dimensionless. And so this feet and this feet are going to cancel. So that brings it down to 1, and then this foot and the other foot are going to cancel. So that gives you 1 over second, and of course this is in radians. So we can just throw radians in its variant. And that's going to be it for question 5. So moving on. Alright, so now for question 6, we want to find the absolute maximum and absolute minimum of this function right here on the interval -1 to 2. And we want to write our final answer, listing both the x and y coordinates of the points. So the way we want to do these is to find the relative minimum and relative maxima on the interval. So let's look at our function. We have f of x, which is equal to 2x cubed plus 3x squared minus 12x. So now let's go ahead and look at our derivative function, which is f prime of x. This is going to be equal to, this is chain rule, so I may go through it a little bit fast. This is going to be 6x squared plus 6x minus 12. And the way we find our extrema is by looking at when our derivative is equal to 0. So let's say f prime of x is equal to 0. This is the same as 6x squared plus 6x minus 12 being equal to 0. And let's go ahead and factor out a 6 from this. We'll get x squared plus x minus 2 being equal to 0. And now here we can factor this quadratic, and that's just going to be x. We need two numbers that multiply to -2 and add to 1. So that's just going to be plus 2 and minus 1. So x plus 2 times x minus 1 equal to 0. So what this tells us is that we have extrema, or critical points. Sorry, I should say. We don't know that they're extrema yet. Critical points at x equals 1 and x equals -2. But now this -2 we don't care about because it is not within our bounds up here. So we can ignore this. The only one we're looking at is x equals 1. And so the way I like to look at critical points to check if they are extrema is by looking at a number line. So I'll go ahead and draw out my number line right here and put a marker at x equals 1. Now what I want to see is what does f prime of x look like before this and after this. So let's just look at that. So f prime of what we want to do is we want to pick values around 1 so we can take a look at its behavior. So an easy value less than 1 is just going to be 0. So f prime of 0, well, that's going to be equal to 0 plus 0 minus 12. Well, that's just minus 12. We don't care too much about the value, just the sign, so this is going to be negative. And now we want a value greater than 1, and we could do 2, but actually I think it's going to be even easier, because if we just plug in 10, because 10 works nicely most of the time. So this is going to be 6 times 10 squared, which is 100, plus 6 times 10, minus 12. And now I'll go ahead and calculate this, but you can probably see this is going to be positive, which is all we really care about. This is 600 plus 60, which is 660 minus 12, which is equal to 648, I think. Yeah, it looks about right, which is clearly positive. So this tells us that we have a local minimum, right, because we're decreasing down to it and then increasing out of it. It doesn't say anything about justifying, so we don't have to worry about writing it out too neatly. And now the last thing we need to check are the endpoints. So let's check the endpoints really quick. Can't spell. So the left endpoint is minus 1, and the right endpoint is 2. And so f of minus 1, well, that's going to be 2 times minus 1 cubed is minus 1, right, because it's an odd power, plus 3 times minus 1 squared is just 1. And lastly, minus 12 times minus 1 becomes plus 12. This is minus 2 plus 3 plus 12, which is going to be equal to 13. And then f of 2, that's going to be equal to 2 times 2 cubed plus 3 times 2 squared minus 12 times 2. This is going to be equal to 2 times 2 cubed is 2 to the 4th, which is 16, plus 3 times 4, which is 12, minus 12 times 2, which will be 24, right? This is going to be equal to 16 plus 12 minus 24. That is going to be, this first bit is minus 12 on the right side here, and then plus 16, that will end up being just 4. And then last thing I just realized, we forgot to find the y value of our local minimum. So let's go ahead and do that here. We'll just say local min. We have that at f of 1, right? And so f of 1, that's just going to be, we could just look at the coefficients, right? Because 1's not going to change any of them. We'll get 2 plus 3 minus 12. And that's going to be equal to 5 minus 12, which is minus 7. And so these are our only possible values. So now we just need to find the biggest one for the absolute max and the smallest one for the absolute min. So the largest is 13. So we can say absolute max, that is at minus 1 comma 13. Then absolute min is at 1 comma minus 7. And I believe that's all I'd ask for. Yep, find the x and y, and that's our final answer. Alright, for question 7, we have a rectangular box with an open top and a volume of 36 cubic inches is to be constructed. The base is twice as long as it is wide. Which should the dimensions of the box be to minimize the surface area of the box? So this is one of our optimization problems, which for me are definitely the hardest. So let's go ahead and draw it out first. We have a rectangular box with an open top. So I'll just draw out a little rectangular box right here. And the top is open, but of course the sides and the bottom are all filled in. And we know that the volume is equal to 36 cubic inches. And of course the volume, let's go ahead and label these. Let's call the bottom down here length, width, and then of course the height can just be the height, h. And we know that the base is twice as long as it is wide. So in other words, length is equal to 2 times the width, or 2w. And now the other thing we're going to need is that the volume, well, that's just length times width times height for a rectangular box, which tells us that 36 is equal to length times width times height. And now the last thing we're going to need is to write out an equation for our surface area. So let's call it S. And because, right, this is what we're trying to minimize. The way we're going to find the surface area is we know that the top is open, but of course the base isn't. So to find the area of the base, and that's just going to be length times width for the area of that rectangle. And then we're going to need 2 of each of these sides, right? So let's say we have the length and height side. That's going to be 2 of those, right? That's this face that's shaded in the front. And then the face on the right side, we're going to have 1 on the right side, 1 on the left side. So there's going to be 2 sides with size, width times height, just like that. And so the first thing we're going to want to do is substitute this L equals 2W equation in. So S is going to be equal to L times W. Nope, I'm sorry. We can actually substitute it in right here. So L turns into 2W times W plus 2 times L is 2W times H plus 2WH. This one doesn't change. And this is going to be equal to 2 times W squared plus 4WH plus 2WH. So rewriting, we get that S is equal to 2W squared plus 6WH. Just like that. And now from here, I want to actually return to this volume equation up here. I'll rewrite it down here though. That 36 is equal to length times width times height, and substitute our L equals 2W in. So this is going to be the same as 36 is equal to 2 times W times WH, which tells us that 36 is equal to 2W squared times H. So let's divide both sides by 2. This gives us that 18 is equal to W squared times H. And now what I'd like to do is divide both sides by W squared. So let's just say H is equal to 18 over W squared. You could divide both sides by H, but this will just make substituting it into our function for S a bit easier. So now let's go ahead and plug in this new equation into S. So we have that S is equal to 2W squared plus 6W, and then instead of H, let's plug in our new equation. We have the H is 18 over W squared. This gives us that S is equal to 2W squared plus, let's see, 6 times 18 over W, right? Because one of those W's is going to cancel. 6 times 18 is going to be 108. So this is equal to 2 times W squared plus 108 over W. And now let's go ahead and take the derivative of S with respect to W. So the derivative of S with respect to W is going to be equal to, well, what is the derivative of 2W squared? That's going to be 4W, right, because we're differentiating with respect to W. And now we have 108 over W, which we can rewrite as, I'll have to go ahead and do it up here. This is 108 times W to the minus 1. In other words, this is 108 times the derivative of W to the minus 1, which is just minus W to the minus 2 by chain rule. So this tells us that the derivative of S with respect to W is 4W minus 108 over W squared, just like that. And now what we want to do is we are looking for hopefully a minimum, right? Because we want to minimize the surface area of the box. So let's go ahead and set this derivative equal to 0. And this will tell us that 4W minus 108 over W squared is equal to 0. And rewriting that, we get 4w is equal to 108 over w squared. And this is, let's go ahead, multiply both sides by w squared. This gives us 4w cubed is equal to 108, and divide both sides by 4, we get w cubed is equal to, let's see, that would be 25 plus 2, 27. And lastly, we can take the cube root, which gives us that w is equal to 3. And so we know that this is an extrema. The last thing we want to check really quick is that this is actually a minimum. So let's look at, let's say ds dw at something less than w equals 3. Let's just say at w equals 1. And this is going to be equal to 4 minus 108 over 1. And this is clearly, actually, we don't even need to calculate it. We can just say that this is definitely less than 0, right? And then if we look at a number bigger than 3, say ds dw, and w being equal to, let's just say 10, because it's going to make things probably easy. This is going to be equal to 40 minus 108 over 100. Again, we don't need to actually calculate this. This is definitely going to be bigger than 0. So in other words, we are decreasing. Our derivative is negative going up to 3, then it increases out. So we're definitely at a local minimum at w equals 3. Now the last thing to do is just find the other values. So we know that L is equal to 2w. So let's go ahead and write that. L is equal to 2w, which is going to be 2 times 3, which is 6. And then the other thing we have to remember is that 36 is equal to LWH. So 36 is equal to LWH. In other words, we have that H is equal to 36 over LW, which is 36 over 6 times 3, which is 36 over 18, which is just 2. So in other words, let's see, how do they want us to write this? Yeah, they just want the dimensions. So we can write that the height is 2 inches. Remember, these are all in inches. The width is in 3 inches. And the length is 6 inches. Just like that. Alright, and that's it. Alright, now for question 8, we want to sketch a graph of a function, f of x, that has the following properties. I won't go ahead and read them out quite yet, because the first thing I want to do is put some tick marks on this graph. So you can see the highest number we have is 4, so we can kind of make tick marks maybe up to 6, let's say. So we'll have 1, 2, 3, 4, 5, 6. Same thing on all these other axes. 4, 5, 6. They don't have to be perfect, because of course we're going to label all the other parts of our graph. 5, 1, 2, 3, 4, 5, 6. And last one on the negative x-axis. Alright, and now let's go ahead and start looking at these. So we have a couple points. We have that f of minus 1 is minus 1. So let's go ahead and put that down right now and label that. Minus 1, minus 1. And also we have that f of 4 is equal to 2. So we have f of 4 is equal to 2, which is right here. 4 comma 2. And now we have the limit as x approaches 1 from the negative side is infinity, and when it approaches 1 from the positive side, it's minus infinity. So that tells you we're going to have a vertical asymptote. Right here, and this is of course at x equals 1. Next up, the limit as x approaches negative infinity is going to be 1, so that's a horizontal asymptote. So we'll go ahead and put some tick marks right here. This is y is equal to 1. And lastly, the limit as x approaches positive infinity is going to be negative infinity, so it's just dropping down really steeply. And now we have all of these limits, or these derivatives. So for these derivatives and problems like these, the way I like to do them is with two number lines. So let's write f prime and f double prime. So let's start with, we have f prime first. So let's write out some key points. For this one we have, let's see, we have -1 and 1, and then 1 and 4. So those are all of our key points. We have a -1, we'll put it right here, a 1, then a 4. So from -infinity to -1, we are negative. From -1 to 1, we are positive. From 1 to 4, we are also positive. And then from 4 to infinity, we are negative, just like this. Now for our second derivative, where are our key points? We have a key point at -3 and 1, and that actually looks like about it. So let's put -3 somewhere down here, so it lines up a bit, and then 1 right here. So from -infinity to -3, our second derivative is negative, so we're concave down. From -3 to 1, we are positive, concave up. And then from 1 to infinity, we are less than 0, so we are concave down. So now, this is all we have, so we can start graphing a bit. So the way we'll start is from negative infinity. So we know we have an asymptote at y equals 1. We are going to be concave down and also decreasing. So that's going to look something like this. And we're going to keep going until we hit -3. And then we're going to switch to concave up. So let's put that somewhere right around there at -3. X equals -3. And now we are concave up, but still decreasing until we hit -1. So we'll make that hit right here at our point -1, -1. And now after -1, we are concave up and increasing, and that is going to go straight into our vertical asymptote right here. And now after we hit 1, we are going to be increasing but concave down. And then at 4, we are going to be decreasing and still concave down. So that's going to be kind of like an upside down parabola as we go up, up, up. Then we're going to have our maximum at 1. Then we're going to go keep decreasing off until we hit -infinity, right, as we said right up here. And that's actually going to be all we need to do for this one. All right. For question 9, we have the figure below, which shows the graph of f prime of x, which is the derivative of f of x. And now we want to answer some questions about f of x. So, part A, for what values of x is the function f increasing? Write your answer using interval notation. So, for this one, make sure you recognize that this is f prime of x, right? This isn't f of x. So when is f increasing? Well, that's going to be whenever this function is greater than 0. So that's going to happen on two intervals. First off, we're going to have from -1 all the way up until 0. That's kind of this portion above the line right here. So -1 to 0. And then we're also going to have from 1, which is right here, and all the way off until infinity, or as far as this graph shows, it's going to go until infinity. So we'll have +1 to infinity. And then we're writing this using interval notation. So I'll go ahead and write a set union right here. And that's it. For part B, we want to find for what values of x is the function f concave down. Write your answer also using interval notation. So when f will be concave down, this tells us right here that the f double prime, or the second derivative, is less than 0. And so to find when the second derivative is less than 0, we can find when the derivative function has a derivative that is less than 0, or basically when is the derivative decreasing. So that's going to be on, let's see, it's going to start decreasing here, and then it finishes decreasing here, and it seems to be positive everywhere else. So we can say that the interval is going to be from the x value of this, which is -0.58, up until over here, which is at x value 0.58, positive. And that is going to be it. And now for part C, at which values of x does the function have a local max? So remember, to have a local max, we have to have a negative derivative up until a point, and then a positive derivative coming out. And so let's go ahead and look at, the derivative will be 0 at our critical points, or at our potential extremis. So let's go ahead and look at each critical point. So over here, we have a derivative that is negative, and then a derivative that is positive afterwards. So in other words, we are decreasing down and then increasing out. So that's a minimum, but we are looking for a local max, so it's not going to be at this point over here. Then the next extrema, we are positive coming up into it, and then we have a derivative of 0, and then we are negative, a negative derivative coming out. And that's actually exactly what we want, so we know we'll have a local max at x equals 0, definitely. And then the last one we have to check, we have a negative derivative coming in and a positive derivative coming out. That's going to be the same thing. We're decreasing and then increasing. That's a minimum, not a maximum. So our only point, or our only value of x where there's a local max, is at x equals 0. Now moving on to question 10, which should be the final question yet. For this one, we want to just solve each of these true or false. We do not need to justify our answers. So for this first one, part A, if f prime of x is equal to everywhere and f of 2 is equal to 4, then f of x is equal to 2x plus 2. So the way we can do this is, I think the easiest way is just integrating this. So we have f prime of x is equal to 2, which tells us that f of x is going to be equal to 2x plus c. And now if we have f of 2 equals 4, well, this tells us that 4 is equal to 2 times 2 plus c, which tells us that c is just equal to 0, right? Because this 4 and this 4 are going to cancel. So in other words, we get that f of x is equal to 2x plus 0, which is definitely not this, so this is going to be false. Now for part B, there exists a differentiable function f satisfying that f of 1 is 3, f of 3 is 9, and f prime of x is greater than or equal to 4 everywhere. So for this one, we're looking at a derivative, and we have 2 points. So this is giving us a hint that we're probably going to want to use the mean value theorem. So let's go ahead and check this out. So let's look at f of 3 minus f of 1 over 3 minus 1. And so this is going to be equal to 9 minus 3 over 3 minus 1, which is equal to 6 over 2, which is equal to 3. And so what this tells us is that by the mean value theorem, so the MVT, we don't need to justify our answers, so I'm not going to write it out too explicitly, but go ahead and review the mean value theorem if this doesn't sound familiar. By the mean value theorem, at some point on this interval 1 to 3, the derivative must be equal to 3. But what it says up here is that the derivative is always greater than or equal to 4, which is a contradiction, right? It's impossible to have those two things true at once, so this must be false. Alright, next up, we have that if f prime of 7 is equal to 0, and f double prime of 7 is greater than 0, then f of x has a local minimum at x equals 7. And yep, that's definitely true, right? If the first derivative is equal to 0, that tells you it's a critical point, and then the second derivative being greater than 0 tells you that it's going to be concave up, so it's going to be something like this. So we're definitely going to have a local minimum there, so that's going to be true. Right. Next up, we have that if f double prime of x is always equal to 4, then which of the following is true? So f double prime of x always being equal to 4, well, that tells us that f double prime is always greater than 0. So in other words, f of x is always concave up. Because remember, it's concave up whenever the second derivative is greater than 0. Now lastly, for part E, if f of x is increasing, a Riemann sum using left endpoints will be an overestimate of the actual area under the curve. For this one, I think the easiest way is to just check. So if f of x is increasing, then there's a couple things it could look like. It could look like this, could look like this, or it could look like this. Now, if we're using left endpoints, well, it'd be something like this. We'd draw it, and then draw it over, and then we'd have another left endpoint, and then draw it over, and then this is the shaded region we're actually looking at. So in this case, it's definitely an underestimate. Let's check the linear case. If we're drawing left endpoints, this is also definitely an underestimate, as we're missing some spots. And then same thing over here. If we draw left endpoints, definitely an underestimate because we're missing some area. So is it an overestimate? No, it's actually going to be an underestimate. So that's going to be false. And that is it. So if you made it this far, nice job.